Okay, then we will start today's lecture, and the talker is the Professor Jair Koiller, and the talk is a poor man's view on Adiabatic Chaos. It's okay, Jair. You can start.
Okay, so thank you so much for the organizers, and especially Hildeberto and Elizabeth that, I knew when I was only 19 years old. And since then, they have been very important in my whole life. So this is the outline. I don't know if I will end up doing everything, but essentially I will first talk about something that stunned the celestial mechanics community in the early 80s, which is a phenomenon that was found by Professor Jacques Wisdom from MIT. And then the explanation needs some preparation. So that's the second topic. And in the second topic, I will stress that random maps appear naturally out of this situation. Then I will go into the explanation by Wisdom, and then I'll go to some historical notes and my personal participation, very little participation in that episode, with some final comments. And I stress that perhaps this subject is 40 years old, but perhaps there's still something that can be done with the diagnostics, like Lyapunov exponents and things like that, in the realm of random maps. Okay, so what is the discovery? The discovery was that by solving some funny approximation of the three-body problem, one could find, by solving for a longer time than people used to do, that suddenly there were jumps in asteroids that were in 3-to-1 resonance with Jupiter. That means that what Jupiter goes one way, the asteroid goes 3 times. And in that situation, you can see that there is a depletion on asteroids. And that was the reason for this depletion in certain resonances was a question for many, many years. And people appeal to different mechanisms, but it's curious that only pure celestial mechanics, the pure n-body problem can, be responsible for it. So Daniel Kirkwood was a nice man. In the overflow, I have some stories about his life. And he guessed that resonance was the mechanism not only for the depletion of certain asteroids between Jupiter and Mars, but also he talked about the rings of Saturn. So we jump to the 80s, and Wisdom was a very young guy. Actually, this discovery was part of his PhD thesis. And 20 years later, he got a very important award, which is the Brouwer Award, which is a prize from the Astronomical Society. He's a very nice person, and hopefully Annette is talking to him. He might give an extra talk in the sequence of seminars. Let's keep our fingers crossed on that. So his first papers came out of his thesis. The first one appeared in March of '82, the second 1 year later in Icarus, and it was based on this mapping. And I can later, if there's time, I can discuss how he derived the mapping. This is not the subject of this talk. I don't want to emphasize how he derived the map, but I would just jump very quickly to some of his construction. He started with the usual canonical elements, and then he expanded, like the equation 2 in the perturbing function in Fourier series. And people in celestial mechanics are very versed on it. There's a lot of work to derive the resonant Hamiltonian, and eventually Wisdom ended up, after doing a lot of simplification, with this very simple looking Hamiltonian. Basically, the most important thing is the big phi is the conjugate variable of little phi. And little phi is basically the resonant angle in some rotating coordinates. And the other coordinates, x1 and y1, are basically related. The radius is related to the eccentricity. So when we show later on some Poincaré mappings, you see that the distance from the origin in the mapping reflects how far the eccentricity can go. So let's keep in mind that this looks more or less like a pendulum, because you have a big phi and a small phi, which is the conjugate variable, and they are modulated by some quantities that are also varying. And if you look at the right-hand side, you see that the coefficients are proportional to the proportion of the masses within the Sun and Jupiter. That's the mu, 1 divided by 1,000. So that's the small parameter. And that shows that somehow this system is kind of a slow, fast system. But this was not used by Wisdom in his first approach. In his first approach, he derived the mapping, and with this mapping, he was able to solve the problem for much longer times. So that's how the mapping was derived. It was based on a trick from a paper by Chirikov that appeared a couple years before. So historically, we can, credit to Chirikov the idea of using mappings in these mechanical systems. So that discovery by Wisdom was first seen with some, skepticism from the community, but after it was confirmed by really solving the three-body problem directly, Wisdom started to be, seen as, a very clever guy, and he started getting prizes. So that was this first prize he got, was the Urey Prize lecture that was around the end of the 80s. And I'm using some slides from this presentation. And in figure 7, you can see that the eccentricity has really some strange sudden jumps. And between the jumps, you can see that there is some kind of fast oscillations. So that indicates that probably the problem has 2 time scales. And about the 2 time scales, we'll talk very much soon. So there's the, how can you use, not solving the equations by some computer tricks, can you use the ideas of dynamical systems to explain this phenomenon? And that was the subject of the 3rd paper that Wisdom published I recall the first ones were in 82 and 83. In 85, he published a theoretical explanation. And I can tell a personal story. I was doing my postdoc at Yale, starting exactly in 85. And at that time, the first two papers of wisdom called the attention of our colleagues in São Paulo, especially Baltazar and Yokoyama. And they told me, if you're going to the US, try to talk to wisdom. And so I did. And wisdom was very, very, he's a very fine man. He was very generous. And he showed me the pictures of the paper before it was even published. And I will continue the story close to the end. So that's the paper that I'm talking about in Icarus in 1985. So what I need to do now is to stop talking about celestial mechanics and go into the ideas of the plasma physics people. So that's the second topic of my talk. So we're talking about problems in general that have two time scales. And this topic that started in the 80s is still going on strong in the plasma physics community. It's keep being used and keep being cited. So I think for young people in our community that perhaps don't know much about it is worth learning about it, how it works. So basically, you deal with a problem which has fast variables, which are P and Q, and it's just 1 degree of freedom for P and Q. There are more complicated phenomena in which fast variables are 2 or more degrees of freedom, but then the resonances are more complicated. Here, P and Q are just in the plane. And Y and X can be in any dimensions, but for our purposes, we will think also in a plane. So you have a system with 4 variables, 2 degrees of freedom, very basic, except that the symplectic form has 1 over epsilon in front of the Y and the X, which means that the equations of motion have the first 2 are fast, and the second equations for Y and X, they are slow. They have this epsilon parameter in front of it. That is more or less reminiscent of relaxation oscillations that were very popular in the beginning of the 19th century by van der Pol and Andronov, except that in the Hamiltonian mechanics situation, there is a more subtle phenomenon. So keep in mind this structure. And just to go ahead of time, going back to wisdom system, let's see if I can go back. Got to wisdom system, my contribution was to put this system in this context. Very little contribution, but wisdom did it heuristically. And my only contribution was to find this epsilon. So I need to go to a very brief review on adiabatic invariants and how they can be being destructed. So I borrowed this from the well-known book by Arnold. When you have a system which has some fast angles and some perturbation, people know how to do the averaging principle, and basically is more like Arnold said, it's an assertion that is not really true, but it's useful. And Gauss, that he has this idea that averaging was to distribute the mass of perturbing planets proportionally to the time around the orbit. It was kind of funny. So that's the only theorem in that chapter of Arnold. And basically, it seems that when you do an approximation in which the average is done, for a long time is a good approximation. And there's some heuristics when you pull a pendulum without looking at it, there is some ratio that is conserved during the whole slow movement. It's the the ratio of energy to its frequency. It is conserved, and that's exactly the action. So that's the adiabatic theorem. If you do the average, when a problem has 1.5 degrees of freedom, so it depends on time, but it varies very slowly. You can prove if the system is integrable. For instance, if it's 1 degree of freedom, the action remains constant. And the proof is more or less simple. It's in Arnold's book. I will not go on the proof, but basically it's not very complicated, but people have done a lot of work to improve the averaging theorem to get a higher order conserved, adiabatically conserved quantities. The problem is that the averaging principle breaks down when in one frequency you are near a separatrix. In other words, the frequency is close to zero. You have a long time to go around the orbit, or when you have two or more frequencies in the P and Q system, they are resonances. And I will only talk about the first phenomenon. And the leader in this field is Neistat, which was not really a student of Arnold, but he became connected, a very close friend of Arnold. And he's now working in England, and is a very nice person as well. And I owe to Neistat a lot of help, a lot of ideas in that time of my career. In the plasma community, the discoveries of Neistat that were in the 70s were rediscovered by groups, two or three more groups of people from plasma physics. John Carey and Dominique Escandi are still working, very active guys in that community. So for young people, I recommend strongly to take a look in this paper. It was an invited paper in nonlinearity. Neistat is one of the editors of nonlinearity, and he has a very easy to read review about his main discoveries in 2019. And that's what he says in the conclusions of this review, that there are very different mechanisms for destruction of adiabatic invariance. And I will only discuss the geometric mechanism, because the other ones require an eye of an analyst. And the geometric one already captures the phenomenon that wisdom discovered. So let's go in the next few minutes to this. And so this is the heart of this talk. How you have some strange phenomena happening in this type of systems. So we are assuming that the fast system has some separatrix of this shape, for instance. Could also have the shape of a pendulum, or if you have a rigid body, in the momentum representation, you can have this usual division of the sphere into these octants or on these lobes. But here you have this figure 8 type, which is very common. So you have 3 regions. You have the left lobe, the right lobe, and the region outside. So keep in mind that picture all the time. And again, you have this fast, slow system. So the first step to do is that you sketch the phase portrait. Then you freeze the slow variables, and you find action angle variables for the fast system. So I and phi are the action angles, and x and y are regarded as parameters. And if you put this into the symplectic form, which is this symplectic form here, you see that you get some extra terms, which are called stuff. And the miracle is that when you do the averaging principle, you can check it yourself. Upon averaging, this stuff disappears because they have sines and cosines, basically, and they disappear under average. And why you don't have secular terms? That's because there are derivatives in this thing. So that means that when you represent the Hamiltonian in terms of these 4 coordinates, I, phi, and x and y, the phi disappears. And that means that this Hamiltonian has I as an adiabatic invariant. And this adiabatic invariant, of course, depends on the energy level and on the frozen values of x and y. I hope that you are following what I'm saying, because this is the heart of the talk. The stuff disappears in this adiabatic approximation by doing the averaging, and the slow system now is now decoupled, in the sense that if you look at the last box, you have x and y only, and there's no phi, it's ignorable, and the action is kept on the initial value. So for each choice of action, you evolve the slow system only in a planar system. So that's very, nice, but there's a problem. So what's the problem? The problem is that perhaps as you evolve the system, the fast variables, they are changing, the phase portrait is changing with x and y, and I is kept constant. And if you are not lucky, perhaps it reaches a situation in which the fast variables are now very close to a separatrix. So if you go back here to this picture, this figure 8 is changing in time as x and y are changing, and the area is kept constant, and perhaps one of the lobes is shrinking, and the area hits the area of the lobe. So you got a serious problem. So how you solve this problem? First, you have to identify where the trouble happens, and it happens on a level curve of a function that I call u. U is called the uncertainty function. I will explain what is this u function briefly, but basically, keep in mind that the values of the slow variables where you can have trouble, they are level curve of a certain function. So you are in trouble when you hit this curve, which is called the uncertainty curve of energy h. Okay? So the idea is to look back at this picture and say, oh, I can find what is the bad energy related to I is the energy of point C, because the energy of point C is the same of the energy of all the lobes. So I go back here, and I basically compute, go back here, I compute the derivatives of the Hamiltonian with respect to P and Q with X and Y frozen. So this is exactly those derivatives. If you solve these equations, they give you the fixed points of the fast system. Okay? But those fixed points of the fast system, of course, they depend on the so-called parameters, which are the slow variables X and Y. So you can solve a system of two equations in 4 variables. So in principle, you can solve for P and Q as functions of X and Y. Got it? So you insert this back in U, in E, and you get this uncertainty function. So this is a calculation that, if you think about it, it's perhaps doable algebraically. If you have a nice function which is polynomial or algebraic or sometimes analytical, you can really do these calculations and find this function U, and then you get all the level curves that you're interested. You fix some energy level, and you find the curve, which is called the uncertainty curve. And I have a small remark that this is a well-known construction in optimization. When you replace the critical points on the function that you're interested, which is called E, you get in optimization something which is called the indirect utility or value function, except that in that context, they are more interested in maxima and minima, not in saddles like we are interested here. So if you are a colleague of somebody in singularity theory, perhaps a nice project will try to find which are the typical curves that you might get out of this construction, which is basically make the derivative with respect to P and Q, find the solutions and put it back. So which kind of singular behavior can you get out of that? That could be a nice little project in that area. So there is something that you can do equivalently if you work with the transformation to action angle variables. You basically say that the utility function or the uncertainty function is exactly the Hamiltonian calculated on the maximum area. And something that I forgot to mention, that people that studied during the graduate level courses, action angle variables, they know that in each regime, sometimes you need to compute a different action angle set of variables, and that gives you in this situation 3 types of functions, one for each lobe and one outside. In the pendulum, you have the librations regime and the circulation regime. So you have 2 types of action angle variables. And soon I will discuss the following function. Keep in mind this last box, which is the Poisson bracket of the area function, which depends on X and Y. Remember that the phase portrait is changing with the slow variables. So you take the Poisson bracket of the area function with the utility function or with the uncertainty function. And we remember that when you do the Poisson bracket, you are basically taking the derivative of one of them and compute it on the Hamiltonian of the other. There's a misprint in this equation. Where you see V, you should put U. I changed notation. So keep in mind that this is going to be a very important function in what follows. So one small remark is that when you compute the slow Hamiltonian, which is the dA dx and dE dy in the right-hand side of this formula, at those special points where you have fixed points of the fast variables, the partial derivatives with respect to P and Q, by definition, they drop. So the derivatives of this function EU, which is I changed the notation to big U, they're exactly the same derivatives of the original function. Is it as if you forgot the chain rule, but you were lucky and the chain rule was not important for doing this calculation? So now are the questions that arise. What do you do when there is a time in which the slow dynamics reaches the uncertainty curve? Can you predict what to do? So there are three questions. Is it possible that the slow dynamics moves along the uncertainty curve for a while, or does it enter and exit in no time at all? It enters and goes out without going in that curve. So what would be the regime? So when you hit this situation, you are more or less in the fast variables in the separatrix, but you can move to the other lobe, or you can move outside. Or if you're coming from outside, you want to ask, if you're coming from outside, which lobe are you going to enter, the left or the right? So that's the questions that you are interested in. And that's the type of questions that will give rise to probabilistic situations. Can you also find the change in the action when the adiabatic principle ceases to hold? That's the type of questions. And in this review of Neistat, he gives very specific answers. And some of them are more complicated because they need an eye of an analyst. But the simplest situation is the one that I will discuss. It's only geometrical. So let's do the simplest of possible situation. That's why I call this talk this poor man's view. So in this poor man's view, we are doing the simplest assertions that one can do. First, that there will be no drift along the uncertainty curve. And what is the argument for that? What would be the heuristics for that? Perhaps in the fast time, the change from one type of lobe to the other type of lobe, or from inside of outside, is more or less quick. So in the slow time, you don't see it. So you jump from one regime to the other suddenly. But I think it's important to check the literature. When you have 2 or more degrees of freedom, this is not true. But I will, assume that this is okay, to assume that there's no drift at all along the uncertainty curve when you change the regime. And the second assertion is that we are neglecting dynamical jumps, which are small jumps that are, shown by Neistat and other people at that time, that they are a small order and geometrically not so important. The geometrical jumps, they are the ones that are related to changing from one lobe to another lobe with different area. So basically, keep in mind that when you change from one lobe to the other, or from one lobe to outside, what you're really doing is that suddenly you are changing the areas, or in other words, the action, by a quantity of order 1. And this is the most important slide and the only formula in this talk. And it's, emphasized in Neistat review. Also, there is an earlier review by Professor Jackson Hart, 1993, I suppose, this review, long ago. And unfortunately, this review is hard to find, the one by Henrad. But it's very long review and very complicated calculations. And what I want to express in this talk is that this formula can be guessed on heuristic basis. So the formula that you keep in mind is the following. You compute this Poisson bracket, and you say that if you're coming from outside and you want to know which lobe the fast variables will go, probabilistically, they are given by this pi, P1 or P2. They are more or less proportional. They are proportional to the proportions of, if that theta 1 is bigger than theta 2, in other words, the biggest area is the one that has the best chance. And what's the heuristic argument? That heuristic argument is that if you put a lot of particles around the separatrix, you invoke Liouville's theorem on area conservation. You invoke a flux argument. If you think about the Poisson bracket, is the derivative of the area with respect to the slow Hamiltonian, which is xu. So is more or less the flux of particles inside that area, or the flux in time, how the area is growing. So that gives you a plausible heuristic argument for using this formula. And Neistat says that in another review that he did, he has a complete derivation in rigorous terms of this formula here. So let's us stare a little bit, and is basically something that is computable. Areas you can compute if you do calculus 2 in general. You compute areas, in calculus 2. And computing function u is basically from your Hamiltonian. You take that two derivatives that I mentioned before, you solve for P and Q, and you put it back. So U is computable. Everything is more or less, if you're lucky, if your Hamiltonians are not complicated enough, you can do it analytically. So you can compute these probabilities analytically. But keep in mind that these probabilities, they vary along the uncertainty curve. So if you hit the uncertainty curve in different points, you're computing this quantity. At that point, you have different probabilities. So what I'm saying that to stop here this long digression is that we enter the realm of random mappings. So what is the idea? you are, say, in the fast variables in a certain regime, you are solving the slow variables. At a certain point, you reach the uncertainty curve. Then you throw a dice according to those probabilities. And if the dice tells you to go to that regime, this is a random, calculation, you have to throw a dice, then you start again. But the Hamiltonian for the slow variables, I insist, might change because the fast variables are in a different regime. So the calculation of the Hamiltonian for the slow variables, for instance, if you have the two lobes and the lobe outside, you have three different Hamiltonians, one for each lobe and one for outside. So you are in the realm in which, if to solve the system approximately, you keep changing the form of the Hamiltonian during the process, which is exactly the realm of this area of mathematics, random mappings. And let me tell you that this area of random mapping started in 1945 with a small note by John Neumann and Stan Ulam that they never published, that they tried to make an ergodic theorem out of compositions of random compositions of mappings. And what I'm thinking, I'm now near the end of our talk. Maybe I need 10 more minutes. I don't want to go beyond 50 minutes. I started 15 minutes after the hour. So let me go until 5 minutes past noon in Brazil. I think if you want to do a fresh look in this topic, you should combine what you know about dynamical Hamiltonian systems with this area of random smooth mappings. And there are diagnostics that are available in that area that one could study, like there are special Lyapunov exponents, etc., for this area. So let's go just quickly to this example, how wisdom explained the gap. So that's the paper. So this is the main thing. Remember one of those typical jump of eccentricities. In the right side, you can see the Poincaré section associated to that with a given energy to that trajectory. And basically, what wisdom did in 85 was to solve with that method and compute the uncertainty curve. The uncertainty curve here has two egg types curves, the left and the right, and there's like he called a certain uncertainty zone. And the other curves that you see here, they are the solutions of the slow Hamiltonian under the different regimes. And the idea, if you just dash the whole area that are caused by trajectories that hit the uncertainty zone, you get a very big chaotic C, which is related exactly to figure 10. Look at figure 10 and figure 12. They're basically the same. So you can explain the phenomenon by the idea that as you hit the uncertainty curve, you might change the regime, the fast variables, and have a different situation in which suddenly you can reach a strong, a big eccentricity. Recall that x and y are basically the eccentricity times a cosine and eccentricity times a sine. So the further you go from the origin in this picture, the bigger is the eccentricity. So this is the explanation. There's another paper by Wisdom in which he he discusses that in more detail. And I recommend, if you want to see what happens after wisdom study, a review paper in 1997 by Michelle Moons, in which she also tells about other work that came after wisdom. So she said what was known before wisdom, during wisdom, and after wisdom. So I recommend very much this review paper. And in particular, there is a paper by Professor Silvio Ferraz Melo and a student, Júlio Klafke, that makes a better mapping. Remember, wisdom did a very simple Hamiltonian. By doing a longer, a bigger, but the method is basically the same. He finds similar results. So let me just use my last minutes to tell a little bit about the story of this topic. And Arnold, in a book that is hard to find, but it's a very nice book, he mentioned 10 discoveries in the 80s, and this theory of the separatrix crossing he attributes to Neistat and Carius and Tennyson as one of the main discoveries in the 80s. And that's what Arnold says. Basically, he gives the reference, and he also mentions Wisdom's paper, which is the sort of the more typical example of the phenomenon. That was actually, if you think about the 80s, that was actually 10 years after the first papers that Neistat did. So one can say that in the West, those papers were not known until the 80s. So this is the paper by Tennyson, Carey, and Escandi. And then Neistat came back in 87, and he used an example, Wisdom Systems. And there is also a review by Escandi, how the story of chaotic nonlinear dynamics is applied to plasma physicists. And I finished by telling that how I entered this area by talking to Wisdom, going back to 85. He told me the story, and the only real contribution is that I realized that you can put this small parameter and do it less heuristically. But nowadays I will not, give too much credit to ourselves. And in fact, we wanted to change the name. Instead of Adiabatic Chaos, we wanted the name Relaxation Chaos, but it never took off. Adiabatic Chaos took off as a name, and Relaxation Chaos doesn't exist. And we are lucky enough that Professor Hildeberto mentioned our paper in his later paper in the late 80s. And Neistat also mentioned something that we found that certain equilibrium solutions that were attributed to Hill and Sinclair, they already appear in Wisdom's Hamiltonian. And what I'm really proud is that my colleagues Tadashi Yokoyama and José Baltazar, they did Wisdom method for other resonances. And Sueli Gillians, which was a student of Roberto Martins, also did a study. So there were some follow-ups from our efforts. And there's some end-up remarks about random mappings. It's a very noble area in dynamical systems. And a mathematician that was very well known in the 50s, Kakutani, he really did the proof that Ulam and von Neumann never published. So Kakutani did. So this area of random dynamic system is going on very strong. And the leader of this area is Ludwig Arnold. So it's not our Arnold, is another Arnold, a lesser Arnold, but still an Arnold. Ludwig Arnold, and he is still alive, I guess. He's in his 80s. And in Bremen, I think he was the leader of this area. And it's a very, important area. And I think if you talk to people from this community, and in Brazil especially, people in dynamical systems, there are people in the Federal University of Niterói that work on that. So I think it's a good idea to try to tie up the dynamics of random transformations with this type of mappings that appear in slow, fast Hamiltonians. So as an overflow, I mentioned that this problem has relevance because humanity can be destroyed either by a virus or, unfortunately, by a nuclear war, which we are in danger now, or by a big asteroid. And you can make your choice, which one you prefer. So that happened last year. And there is an event that is going to happen in October that they are trying to divert a small asteroid to see if they can really do it. And this is more or less the end. I went up with an animation. So I don't think this phrase is really by Poincaré, but if not, let's pretend it is that every mathematician has to work at least once in his life in the three-body problem. So I went up with this animation. I don't know if it's going to appear because it might appear in my screen and not in your screen. I'm not sure. But I'm going to send you the slide. Anyway, thank you so much.
Thank you, Jair. Thank you, Jair, for the excellent talk. Then we will start the question section. Someone has a question for Professor Jair? Can you hear me?
Yes, sir.
I do.
Okay, someone have questions, comments about the Professor Jair's lecture?
Okay, I can.
Okay.
Hello? Hello?
Okay. I can hear you.
Okay, my question is not exactly on the techniques that Jair has exposed. It's a little bit more general. I would like to know his opinion on the fact that none of the methods used to solve the 3-to-1 gap worked on the 2-to-1 gap.
The 2-to-1, as I understood, has a peculiarity that instead of repelling, somehow it attracts asteroids. And I think the person that could give you an answer, I refer to Professor Silvio. I think he's around. Can Silvio answer that?
No, I'm doing the question.
Ah, you asking the question. I see, I didn't see. So you ask the question and please,
I know the answer.
so please give us the answer, please. I pray.
It's not easy. It's not easy to get the answer in one word. The problem is that in the three-body problem, Sun, Jupiter, asteroid, the 2-to-1 resonance is not unstable as the 3-to-1 resonance.
Yeah.
Chaos has completely different nature in that resonance. So if you apply every method that we apply using the model Jupiter, Saturn, Sun, Jupiter, asteroid, leads to very regular motions. even for high eccentricities. There is a small zone of chaotic zone at low eccentricities, but this zone is confined, and the orbits are not able to escape from it to the more eccentric regions. The only way to explain the 2-to-1 resonance is to include Saturn in the model. So we have to go to four-body problem, not only three-body problem.
Okay, very nice. Thank you.
Professor Silvio finished, right? Then someone have some question or comment about the Professor Jair lecture? No? Then we will thank Professor Jair.
Thank you.
I have some comments from the organization. Then we have been doing the Matemairacorana for over 1 year. Then we celebrate Hildeberto's birthday. We have excellent lectures, scientific dissemination, and interaction between friends during the pandemics. Naturally, the number of talkers is decreasing. Then, for this reason, we announce the end of the Matemairacorana in the regular format. From now on, we will hold the event when we have demand for speakers. We expect to have 2 lectures every 2 months. The lectures will be done on Thursdays at the same time as usual. And I hope we continue to see each other with some regularity. Then this is the announce for the organization, and Annette have some words to talk. Annette?
I have a video for you, a small vignetta. Okay. Okay, I will play this. Pode entrar. Pode entrar. Ó. Could you hear the audio?
Yes, Annette.
Okay, sorry. I will start again. Sorry, I hear something. I don't know what happened.
The audio is not so good.
No? Where? Yeah, like this?
Maybe yes.
Okay, I will try again.
It's not so good yet.
Yeah, I will change something with this. I don't know where are you. I don't know where. Sorry.
Maybe if you send the video for Jair can play the video.
I don't know where you are. I don't know. I don't know. I lost your window actually. Are you? I can hear you, but I can't see where you are. Guys, I have a problem.
Não tem no file, não.
Não tem aqui. Não tem.
Pode encaminhar como
Não consigo. Eu não consigo encontrar.
Anete, o teu som pode estar alto aí, gerar eco. O teu som parece que está gerando interferência ou eco.
Tá.
Teu som.
Eu tô procurando a janela de vocês, que eu não tô achando. Vocês sumiram daqui. Esse é o problema. Cadê?
Entra e abre de novo.
Eu não tô achando a janela para entrar de novo.
Esse vídeo tá no Drive?
Não. Essa era uma outra janela. Me tira da reunião, Lúcia, por favor. Hear me. Hello, can you hear me?
Yes, Annette.
Oh, thank you. I will try again. Wait a minute. I will to mute here.
Preciso colocar o PDF, Annette.
Tá conseguindo, Cláudio?
Não, a tela pega todo e não deixa abrir no PDF.
You don't see the presentation?
I think just wait 1 minute. It will come out. Okay, it's coming.
Okay, it's coming? Okay.
Yeah.
Last we have the idea of the camera.
Muito bom, né? Great video.
That's all, guys. Thank you very much.
Congratulations, Nanette.
Okay, I will stop to recording. I don't know, somebody want to say something. I don't know if you want to say something also.
Well, I guess thank the whole committee for all the work and dedication. I think you deserve a big applause.
Thank you very much, Eduardo.
And of course, also to say that nothing of it could be possible without Professor Hildeberto Eulálio Cabral being our, center of universe, so to speak.
Okay, I will start to record to take a picture from today. So if you want to turn on your cameras.
Okay.